Okay, we're going to finish up chapter 7 today. So please have your guided notes out, chapter 7 guided notes. I would also ask that you have a roadmap available somewhere nearby and a calculator. So guided notes, roadmap, and a calculator. All right, let's finish up the chapter. We left off talking about this. So moles of a compound. So we're going to talk about that. Consider the water molecule H2O. So if we look at this, so H2O, I'm going to ask you some questions about it real fast. Okay? First one, how many atoms are in one water molecule? How many total atoms? Well, yeah, we've got how many hydrogens? 2. And how many oxygens? 1. So there's 3 total. There's 3 total atoms. Okay? Second question, let me ask you this. How many atoms are hydrogen? 2. Yeah, here's hydrogen, and we've got 2 of them. So the answer there is 2. Now, final one. How many atoms are oxygen in one water molecule? How many of them are oxygen? Well, just 1. Okay. And so we're going to use this. This is kind of a ratio. You've studied ratios in math. But the ratio is a comparison of 2 numbers. The ratio of hydrogen to oxygen in a water molecule is 2 to 1. Okay. That means 2 hydrogens for every 1 oxygen, correct? So another way of saying this is there are 2 moles of hydrogen for every 1 mole of oxygen in a water molecule. Again, because that ratio is 2 to 1, there's 2 hydrogens for every 1 oxygen. We can also say that there's 2 moles of hydrogen for every 1 mole of oxygen in a water molecule. The ratio is 2 to 1. Okay, let's do a few practice problems to see if we can make sense of this. Practice problem number 20. It says, determine the number of moles of hydrogen in 2.5 moles of water. Okay, let's follow the same 3 steps that we've been doing this whole chapter. Step 1, we're going to underline what they give us. What are they giving us? 2.5 moles of water. Let's write actually the formula for water. What is it, guys? H2O. Okay. What are we circling? What does it want us to go to? Moles of hydrogen. So circle moles of hydrogen. Okay, step 2, we're going to write down what they give us, 2.5 moles of H2O, and put it over 1. Okay. Now, this is where it gets a little different. It says moles of water, and it wants to go to moles of hydrogen. So if you come to the roadmap, are we ever going to leave this box? No, we're staying here. We're staying at moles. But we need to convert moles of water to moles of hydrogen. So we're going to do that with one conversion factor here. Okay? If you have moles of water on top, what's got to go on the bottom? Moles of water. That's how we get it to cancel out. Well, let's make our own conversion factor again. In 1 mole of water, how many moles of hydrogen are there? There's 2, because there's 2 hydrogen atoms for every 1 water molecule. So we're just going to say 2 moles of hydrogen. Goes on top. Now let's cancel out units. Moles of water divided by moles of water is 1. So they cancel out. And I'm left with moles of hydrogen, which is exactly what we wanted. Okay, so I can stop there, throw on an equal sign. What's 2.5 times 2, guys? 5 what? My units are moles, and what substance are we talking about? Hydrogen. So that's how you will convert from moles of a compound.
Why would there be more moles of hydrogen than there is moles of water total?
Okay, good question. Why is there more moles of hydrogen than moles of water total? Because here's the answer. It goes back to that ratio. Okay, a ratio is a comparison of 2 numbers. For say we have 1 water molecule. How many hydrogens do we have? We have 2 hydrogens. So because there's in one water molecule there's 2 hydrogens, so if you look at H2O, in one molecule there's 2 hydrogen atoms. And so you just times it by 2.
I just thought it'd be like 2/3 of the, like 1 mole of water would be hydrogen.
Oh, I see what you're doing. Okay, yeah. Does this make sense though, what we did?
Yeah.
Okay, I would do it this way. Okay. So in 2.5 moles of water, put your moles of water down here, and there's 2 moles of hydrogen for every 1 mole of water. Okay, good question though. All right, let's go to, we got it right. It's 5 moles of hydrogen. Let's go to practice problem 21. Okay, let's get the hang of this. It says determine the moles of chlorine ions, so Cl minus ions. Just as a review, if it's Cl minus, what kind of an ion is it? A cation or an anion? This is an anion. Remember, cats are positive, right? So this is a negative, so this is an anion. Anyway, that's just a review. Determine the number of moles of chlorine ions in 2.5 moles of zinc chloride. What are we underlining? Yeah, 2.5 moles of zinc chloride. What are we circling? Moles of chlorine ions. Okay. Step 2 is write down what they gave us and put it over 1. Okay. Now let's look at the roadmap. We're at moles, so we're right here. But it also wants us to go to moles of chlorine, so we're not going to leave this box. We need to come up with our own conversion factor to get there. So let's do that now. Okay. Here's an easy way of thinking about it. If moles of zinc chloride is on top, we know that it's got to be moles of zinc chloride on the bottom. Well, in 1 mole of zinc chloride, guys, how many chlorine ions will there be? Well, you look at the Cl, how many are there? 2. So I'm going to put 2 Cl minus ions. 2 chlorine ions. Okay? Now, my moles of zinc chloride cancel out. I'm left with ions of chlorine. Oh, I guess we should put moles. Moles of chlorine ions. Okay, and then I'm left with the units that it wanted here, so I can just put on an equal sign. Again, what's 2.5 times 2? That's 5. Okay, 5 what though? Moles of Cl minus ions. Very good. Okay, so really not that difficult, is it? It's just practice with making your own conversion factor when we need to. Okay, practice problem number 22. I want you guys to try this one on your own. So if you're watching the video, please hit pause right now. Try this one on your own. Once you have your answer, hit play and see if you got it right. Okay, guys, let's see how you did with this one. Hopefully, you underlined 1.25 moles of glucose, which is C6H12O6, and you circled moles of carbon. Okay? Step 2, we're going to write down what they gave us. So 1.25 moles of glucose over 1. Now, if we go to the roadmap, we're already at moles. And it wants us to convert to moles of carbon. So again, we're not leaving this place on the roadmap. So we're going to have to come up with our own conversion factor, which we'll do now. Okay? Remember, if moles of glucose is on top, it's got to go on bottom. That's the first thing you should always look for. Whatever is here, it's got to go down here. In 1 mole of glucose, how many moles of carbon do we have? Well, there's 6 carbons there, so it's 6 moles of carbon. Goes on top. Okay, my moles of glucose canceled out, and it left us with moles of carbon, which is what we wanted. So let's throw on an equal sign. And 1.25 times 6. Did you guys get 7.5? Okay. 7.5 what? Yeah. Moles is my unit, and the substance that we're talking about is carbon. So you need all of that in order to get the answer right. Who got it right, just by the show of hands? Okay, good job. I think I've got one more problem like this, so let's get to it. Practice problem number 23. Let's read it. It says, determine the number of sulfate ions in 3 moles of iron sulfate. Okay, this is called iron sulfate. So I'm going to give you a second to try this one. Sulfate, I'll just give you a hint, is a polyatomic ion. It's SO4. So this is the sulfate ion. But how many do we have? 3 of them. So that's kind of my hint. Try it. If you're watching the video, please hit pause. Try it on your own. Hit play once you have your answer. Okay, let's see how you did with that one. Hopefully you started by underlining 3 moles of iron sulfate, and then you circled number of sulfate ions. Okay? So we've got 3 moles of Fe2 parentheses SO4 parentheses 3 for iron sulfate. Put that over 1. Okay. Okay, we're at moles, and we want to go to the number of sulfate ions here. Now this one's a little bit different, isn't it? It didn't say the number of moles of sulfate. This one's the number of sulfate ions. Okay, well, where do we see ions at over here? Okay, it's in the particles box, isn't it? Okay, so we need to go from moles up here to particles. So let's do that. Okay, we got my conversion factor. I need to times it by this top one to get over to ions. So we've got Avogadro's number on top, and I've got 1 mole on the bottom. Now on the roadmap, it doesn't tell you the substance because that changes from problem to problem. But if moles of iron sulfate's on top, we've got to put moles of iron sulfate on the bottom. Now, this is where we have to pay attention. Is Fe2 parentheses SO4 parentheses 3, is this an ion or is this a compound? This is a compound. So I'm going to put Avogadro's number of Fe2 parentheses SO4 3 iron sulfate compounds. Okay? So what I just did right there was get over to compounds first. Now, from there, we can take it, create our own conversion factor to go to sulfate ions. And this is how I would do it. Okay? If iron sulfate compounds is on top, I'm going to put that on bottom. Okay, in one of those guys, in one compound of iron sulfate, how many sulfate ions do we have? How many sulfate ions do we have in one of these guys? There's 3. This 3 right here tells us there's 3 of the sulfate ions. So 3 SO4 ions, sulfate ions. Okay. So let's cancel out like units. Those cancel. Moles of iron sulfate cancel out. And now I'm just left with sulfate ions. Okay. So let's times across the top 3 times Avogadro's number times 3. And then there's just 1 on the bottom, so this is my answer. Did you guys get this? 5.42 times 10 to the 24th sulfate ions. Okay. Very good. All right, I've got practice problem 24, and it's got 2 parts to it. This is about as hard as a problem as I could think of to finish up the chapter with. So this will be our last practice problem in this chapter. I would like you guys to try it on your own first, okay? So let's read it. It says, a sample of carbon dioxide, which is CO2, has the mass of 52 grams. there's two parts. There's A and B. And so I would like you to answer those. On part A, how many carbon atoms are present? And B, how many oxygen atoms are present? So take a second, see if you can try a problem like this on your own and get it right. Okay, let's see how you did with this problem. If I was you, I would have underlined 52 grams of CO2. And then on part A, what we're trying to get to is the number of carbon atoms. So I would have started out part A like this. So 52 grams of CO2 and put that over 1. Okay? We're at grams. You're right here on the road map. Okay, we want to go to atoms of carbon, so we want to come up here. There's no shortcut. We've got to go through moles. So let's find the bridges here that we're going to cross. We need to times by that conversion factor. Once you get to moles, you're going to come up here and times by this conversion factor to get up to particles. So that's my plan. Let's see if we can figure this out. So the first conversion factor is set 1 mole over the molar mass. 1 mole. Now the substance that we're talking about in this problem is CO2. If grams of CO2 is on top, I need grams of CO2 to be on the bottom. Now, molar mass. Where do we find it, guys? Periodic table. If you look up carbon, it's 12. But we've got 2 oxygens as well. So oxygen is 16, but there's 2 of them. Did you guys get the molar mass was 44 grams?
Yeah.
Okay, good. Now my grams of CO2, it cancels out. I'm to moles. So what we did right there was just get to moles. Can't stop there though. Let's come over to particles. We need to times it by 6.02 on top. Avogadro's number 6.02 times 10 to the 23rd. And 1 mole goes on the bottom. The substance we're talking about is CO2. Now, is CO2 an atom or is it a molecule? Yeah, it's a compound or a molecule, right? This is actually a molecule because they're both nonmetals. So this is a molecule. So when I put Avogadro's number of something, it's going to be molecules of CO2. Okay. Now my moles of CO2 cancel out. Now can I stop at molecules of CO2? The answer is no. I need to go to carbon atoms. So I'm going to create my own conversion factor right here to finish this off. If molecules of CO2 is on top, it's got to go on the bottom. Let's make my own conversion factor. In 1 molecule of CO2, how many carbon atoms are there? Yeah, there's just 1 carbon, because there's just an implied 1 right there. So 1 carbon atom. Okay, and now I'm done, because my molecules of CO2 cancel out. I'm left with carbon atoms. Okay, so let's solve that with a calculator. Did you guys get this? 7.11 times 10 to the 23rd. Did anyone else get that? Okay. What are my units going to be? Atoms. And my substance that I'm talking about? Carbon. So that's how many atoms of carbon would be in 52 grams of CO2, which is kind of cool. We can figure that out, right? Now let's go to part B, okay? It says how many oxygen atoms are present. Let me see if I can speed this up, guys. On part B, we're still starting with 52 grams, right? Is the molar mass going to change? No, it's still CO2. Everything's going to be the same until you get to this last conversion factor, right? On this last conversion factor, in 1 molecule of CO2, how many oxygen atoms are in 1 molecule of CO2? 2 this time. So there's 2 atoms of oxygen. Okay? So everything's the same from there to there, and then we just add this last conversion factor. Okay, let's get a number for that. So 52 times Avogadro's number divided by 44. Did you guys get this number? 1.42 times 10 to the 24th?
Yeah.
Yep. And what's my units going to be now? Atoms of what? Atoms of oxygen. Very good. Okay. I mean, that's about as hard a problem, as difficult a problem as I could ask you in this chapter. So if you can logic through that one, if you can follow me through there, all those conversion factors, you've got this stuff. Okay. I think you guys are doing great. So that's it. Now there's just one more small section in this chapter. I would like to finish it now. So we won't do these extra problems, but here's the part that I wanted to finish up on. Formulas. Okay, let's talk a little bit about formulas. So formulas like H2O. Is that a formula? Sure. Okay, it's a formula for water. Well, there's two different types of formulas that you can see. The first one is called a molecular formula. In your book, you're supposed to write the definition. So take a second and write that in. For molecular formula, it's the true number of atoms of each element in the formula of a compound. So it is the true number of atoms of each element in the formula of a compound. When I was going through chemistry and I learned these, I learned it this way. So if this helps you, great. But by molecular in the margins, put actual. Write actual. It's the actual numbers of each element in that formula or compound. It's the actual numbers, what you really have. Okay, let's contrast that, and it'll make more sense here in a second. Let's contrast that to the other type of formula that you will see. It's called an empirical formula. An empirical formula, you're supposed to write the definition, is the lowest whole number ratio of atoms in a compound. The lowest whole number ratio of atoms in a compound. The lowest whole number ratio of atoms in a compound. Okay, now in the margins, by empirical, I want you to write this. This is how I remembered it anyway. It's reduced. That's all that definition means. It's the reduced form. So how do you get an empirical formula? Well, you take a molecular formula and you reduce it. And you've gotten an empirical formula. Okay, so here's what I mean. If the molecular formula was C6H6, can 6 and 6, can that be reduced? Yeah, they're both divisible by 6, so if we divide both of them by 6, don't we get CH? And so your empirical formula is just CH. This is the molecular formula. This is your empirical formula. Okay, so see how on molecular I said it was the actual? We actually have 6 carbons and 6 hydrogens, but on the empirical formula it's the reduced form. It's just CH.
Why do you have the 6 with the first one?
Well, that just tells you that there were 6 carbons and 6 hydrogens. So you could be more specific and say that. Okay. But the empirical formula is really going to be CH. So that's your real answer for empirical formula. All right. Formulas for ionic compounds are always going to be empirical. Remember, ionic compounds have a metal and nonmetal. And we did that. This is when we did the crisscross formula and we reduced them. So they're always going to be reduced anyway. Okay? An example, sodium chloride. Can you reduce a 1 and 1? No, it's the empirical formula. What about magnesium chloride? Can you reduce a 1 and 2? Nope, it's already 1's as low as it can go. Again, it's an ionic compound. It's already reduced. Okay? What about aluminum sulfate? Can you reduce a 2 and a 3? Nope, it's already reduced. Potassium carbonate, 2 and 1 is not reducible. It's already, so if it's an ionic compound, you don't have to worry, it's already reduced. Formulas for molecular compounds, they might be empirical. They might be already, but sometimes they're not. So let's go through some examples, okay? Water. What is the empirical formula for water going to be? It's still going to be H2O. Why? You can't reduce it. The 1 on this for the oxygen is already as low as it can go. So it's still H2O. Okay. Okay, let's go to glucose now. Can you reduce glucose? Yeah, so what's its empirical formula going to be? Aren't all of these divisible by 6? So this one's, isn't it just going to be reduced to C? 1, H what? 2, and the O, it's just a 1. Okay? So, let me see if I can go back. Glucose is a fancy way of saying sugar. It's a type of sugar. And if you look at a nutrition facts label, sugar is classified as what kind of nutrient? Aren't they called carbohydrates? Sugars? They're carbohydrates. Here's why they're called carbohydrates. The C in here is for carbon, carbo. The H2O is a what? Hydrate. It hydrates it. So H2O is water, hydrate. So it's called a carbohydrate. What it means by carbohydrate is sugar. Okay. Here's another type of sugar, but can you reduce this one? No. So the empirical formula is going to be the same. Yeah, you can't reduce it, so its empirical formula is going to stay the same. So again, this is what it actually is. And this one is what? Reduced. Okay. If you remember that, it's pretty easy, correct? All right. Okay, we're done with chapter 7. There's a short summary that I would like to go through. This, what did I call this the whole time throughout the chapter? This is the roadmap. So there's a spot in your guided notes where you're supposed to fill out the roadmap. So put particles here. Put mass in grams in this circle. Put moles over here. And yes, I would like you to fill in these conversion factors. And it does matter which way you go, so watch the arrows and make sure you get the conversion factors correctly. Okay, so hopefully you took a second and filled in your roadmap. Guys, we should almost have this memorized by now. I hope that you will be able to get to the point to where you don't need a roadmap. But I think as you're learning about it for the first time, this really does help. Okay, one last slide where we summarize this chapter. It says, in chemistry, the mole is used to report what? The amount of something. So the mole measures the amount of something. It's an SI base unit that measures the amount of something. Okay? And just like the term dozen refers to 12, what does mole refer to? This number, this very famous number in chemistry, 6.02 times 10 to the 23rd particles. So if you've got 1 mole of carbon, you've got 6.02 times 10 to the 23rd particles or atoms of carbon. Okay, particle is a generic term. It can mean atoms, molecules, compounds, ions. It can mean a lot of different things in science. So just realize that. Okay, and then finally, this number, 6.02 times 10 to the 23rd, it's the most famous number in chemistry. And what's it called? Avogadro's number. Avogadro was the Italian scientist who figured out there was 6.02 times 10 to the 23rd particles in 1 mole. Guys, that's chapter 7. Hopefully that makes sense, and hopefully this has helped you.